Okay. Hi, Lina.
Hi.
Well, so we can start, I think, Jovira
Yes,
Lourdes.
yes.
So it's a big pleasure from my personal point of view to introduce in the non-associative algebra seminar, Professor Dijana Ilišević. Well, I should say that Diana is an active mathematician, not only doing mathematics, but also helping the mathematical community in Europe, and also producing very nice papers and results. I know her since few years ago, so I know she's very active. She's researching on functional analysis, essentially, that's the main topic, but also doing problem on invariance, operator theory, linear algebra, all these kind of steps of stuff that we all enjoy researching. She's even a very nice person, so we cannot measure that aspect in her personal life, but whenever you contact her, you can always get this smile and a positive answer trying to help other people. So finally, in order to give the podium to her before finishing my speech, I would simply say that if you want to take a look of her research, independently of what she's presenting this afternoon, I would suggest you to take a paper by Professor Ilišević, by Dijana, on Mladic and Turnsek on phase isometries, published in Linear Algebra and Application in 2021. It's a beautiful example of what they are doing there. I enjoy it a lot, and I think any reader can do that. So, Diana, it's your turn. I'm happy to introduce you here. Thank you.
Thank you very much, Antonio, for this really, really nice introduction. I'm going to share my screen, so I hope that everything will work. Okay, I hope that now you can see it. Okay. So
Diana,
once again,
okay.
Yeah.
Perfect.
Is it
perfect.
okay?
Yes, it is okay.
So now I would like to thank all the organizers for giving me the opportunity to present my work obtained jointly with several colleagues. My primarily research interests are in operator theory, recently in isometries, the eigenvalues, and eigenprojections. During my research in isometries, I found out that there was a beautiful non-associative structure known as a JB star triple, in which isometries have particularly nice form. And my plan today is to show you how JB star triples are an appropriate setting for studying isometries on various spaces. First, let us recall that an isometry between two norm spaces is a mapping that preserves distance between any 2 points. Notice that we do not assume linearity in advance. But if we assume that an isometry is linear, then it is naturally called a linear isometry, and it is a mapping that preserves norm. There are many interesting problems that are related to isometries, and one of the most important ones is to explicitly describe isometries on a particular space. In this talk, we shall be interested in surjective isometries and their spectra, not only linear isometries, but also nonlinear isometries. However, when we have a surjective isometry, we cannot be very far from linearity. Namely, if we have a surjective isometry that fixes the origin, then it must be a real linear mapping. This celebrated result by Mazur and Ulam is obtained as response to a question raised by Banach. And if we study, for example, the function space, the function algebra C0 of omega, which is the algebra of all continuous complex valued functions on a locally compact Hausdorff space omega vanishing at infinity, then any surjective linear isometry between these two spaces, the two spaces of this type, is a weighted composition operator, where the composition is induced by a homomorphism between Hausdorff spaces, and the weight function is the function with values in the complex unit circle. The first version of this theorem appeared in Banach's book in 1932, but for real-valued functions on compact metric spaces. And this result was extended by Stone 5 years later for real-valued functions on compact Hausdorff spaces. And now we know that it is true for complex-valued functions on locally compact Hausdorff spaces. This theorem is now known as the Banach-Stone theorem. The algebra C naught of omega is an example of a commutative C-star algebra. And in fact, any commutative C-star algebra has this form. Recall that a C-star algebra is a complex Banach star algebra A, star denotes involution, such that it satisfies the so-called C-star equality. The norm of A star A is the norm of A squared for all A. Some C-star algebras are unital and some of them are not, but they can be embedded. Any A C-star algebra, which is non-unital, can be embedded into a unital C-star algebra M of A, the so-called multiply algebra of A, as an essential ideal. For example, the multiply algebra of C naught of omega is the algebra of all bounded continuous functions on omega. The multiply algebra of all compact operators on a complex Hilbert space H is B of H. And in C-star algebras, there is a class of mappings that is really closely connected to isometries. And these mappings are known as Jordan star homomorphisms. An operator J between two C-star algebras is called a Jordan star homomorphism if it is linear, preserving squares, and preserving involution. If it is bijective, then naturally we call it a Jordan star isomorphism. So because of linearity, the property of preserving squares is equivalent to the property of preserving Jordan products. This is why this mapping is called a Jordan star homomorphism or a Jordan star isomorphism. For example, a Jordan star isomorphism between two spaces of the form C naught of omega is a composition operator, where the composition is induced by some homomorphism of the underlying Hausdorff spaces. Jordan star isomorphisms of B of H can have one of the following two forms. Either X maps to V star XV for some unitary V in B of H, or X maps to V star X transposed V for some fixed unitary V in B of H. And the transposition in B of H, even when H is infinite dimensional, can be defined analogously as in the matrices with respect to fixed orthonormal bases. So we can also study surjective linear isometries of B of H. They also can have two possible forms. Either X maps to UXV for some fixed unitary U and V in B of H, or X maps to UX transposed V for some, again, fixed U and V. And in both cases, we in fact have a Jordan star isomorphism, which is multiplied by a unitary. And it is not only the case for B of H, it is the case for any unital C-star algebra. Namely, if we have a surjective linear isometry between two unital C-star algebras A and B, then such an isometry is a Jordan star isomorphism multiplied by a unitary element in B. This is famous Caddison's extension, a non-commutative extension of the Banach-Stone theorem. And this result is true even if we omit the assumption that A and B are unital, but at the cost that this unitary element U is no longer in B, but in the multiplier algebra M of B. So here we notice how closely surjective linear isometries are connected with Jordan star isomorphisms. And it is going to be even more obvious in the case of JB star triples. A JB star triple is a complex Banach space V, together with the continuous triple product on V, which is linear in the outer and conjugate linear in the inner variable, which is symmetric in the outer variables. And for all A and B in V, it satisfies this identity, which is sometimes called the main identity or the Jordan identity, where we have introduced the notion of the box operator A box B, which sends X to the triple product of A, B, and X. Furthermore, for any A, the operator A box A is Hermitian with non-negative spectrum. And finally, the norm of the triple product of A, and A, of the norm of A cubed, is the norm of A cubed to the power of 3. So in this definition, we have Hermitian operators on complex Banach spaces. So recall that a bounded linear operator T on a complex Banach space X is said to be Hermitian if E on I phi T is an isometry for every real number phi. Hermitian operators are very closely connected to isometries, as we are going to see. Not only that isometries appear in the definition, but Hermitian projections will appear as eigenprojections of isometries. First of all, let us emphasize that any C star algebra can be considered and observed as a JB star triple with respect to the triple product which is defined by this formula. So one can ask, and it is a natural question, why to study C star algebras equipped with this, let's say, strange triple product when they have a nice binary algebra product? Sometimes there are advantages of this approach. I'm going to show you one of them. It is known that every positive element of a C star algebra has a unique positive square root. But any element of a C star algebra has a unique cubic root. Some important examples of JB star triples are given here. For example, B of HK. When H and K are equal, we have a C star algebra. We have B of H equipped with the binary product. But if H and K are not equal, then we cannot define a binary product on B of HK. So this is why we have and we need the triple product. Furthermore, since we have the transposition in B of H, we can define skew symmetric or antisymmetric and symmetric operators in B of H. We know how to multiply them, but the result is not necessarily in A of H, that is in S of H. But A of H and S of H are also JB star triples with respect to the same triple product as appeared for C star algebras and for B of HK. And there are also some other examples of JB star triples. In fact, all these examples here are known as Cartan factors. And I would say that these of the type 4, 5, and 6 are more exotic because, at least for me, because I work in operator theory, and for me, the first 3 types are the most important. And now the central result, the description, the characterization, in fact, of bijective isometries of JB star triples. A bijective linear operator T between 2 JB star triples is an isometry if and only if it preserves the triple product. So you can see how nice this result is. It is a beautiful result because on one hand, you have a topological property of being an isometry, and on the other hand, something which is purely algebraic, the property of preserving the triple product. So it is a really nice connection between isometries and isomorphisms, which is something that we have already observed in the Banach-Stone theorem, then in the Caddison's non-commutative extension of that theorem, and also in the generalization given by Peterson and Sinclair. And this result is very useful in studying the spectra of isometries, not only on JB star triples in general, but on some particular examples of JB star triples, as we are going to see. But we shall not be interested only in isometries in general. A special emphasis will be given in periodic isometries. So let us recall that the linear operator T is said to be periodic of period M if T to the power of M is identity and T to any power less than M is not the identity. Clearly, any periodic linear operator is surjective, and the spectrum of a periodic linear operator of period M is contained in the set of nth roots of unity. So in particular, it is finite. In general, for a general isometry, linear isometry, we know that its spectrum is contained in the complex unit circle. But here we can be even more precise. If an isometry is not surjective, then the spectrum is the closed unit disk. So when we have a periodic isometry, then we have isolated points in the spectrum. And every isolated point in the spectrum of a surjective linear isometry is an eigenvalue of that isometry with a complemented eigenspace. This is a result from a short paper by Kellen and Rosenthal. And in fact, they don't give the proof for this result. In their paper, they refer to another paper of a different author, but after detailed inspection of that other paper, it seems that the results of that other paper cannot be applied to this case. And Shiho Oi had the same opinion of this fact. So together with her co-author, she decided to give a new proof of this result by Kellen and Rosenthal, and they even succeeded in generalizing this result to the so-called power-bounded operators. So it is not only for isometries, but for power-bounded operators. This is a recent paper. I think that it was published in May, so like 4 months ago. But this result, that an isolated point in the spectrum must be an eigenvalue, is not true in general. Here we have a very simple counterexample. We have the Volterra operator, which has only one point in the spectrum, 0. But 0 is not an eigenvalue of the Volterra operator. So now let us assume that we have a linear isometry with finite spectrum. We can think of periodic isometries. Then every element in the spectrum, every point in the spectrum is an eigenvalue of that isometry, say T. If Pi is the projection onto the kernel of T minus lambda I times the identity operator, and projection here means an idempotent, then all these projections, the so-called eigenprojections, are mutually orthogonal in the sense that their product is 0. They sum up to the identity operator, and there is the spectral decomposition of T, which is given as a linear combination of eigenprojections with the corresponding eigenvalues as coefficients. And it is not so difficult to verify that all these eigenprojections have norm 1. In other words, they are bicontractive projections. But if an isometry has two-point spectrum, then these two eigenprojections are complemented to each other, and they both have norm 1, which means that they are both bicontractive. And the class of bicontractive projections, as we are going to see, is also very closely connected with isometries. So first, what can be derived from de Kaup's generalization of the Banach-Stone theorem? If we have a surjective linear isometry of a JB star triple, so that the spectrum of that isometry is finite, lambda 1 to lambda n, then one of the following holds. There exist indices I, j, and k, so that j is not equal to I and not equal to k, such that lambda I times the conjugate of lambda j times lambda k is also in the spectrum. Or all eigenprojections of T are Hermitian operators. I believe that this result can be improved because it doesn't say much if we have a lot of eigenvalues. But if we have two eigenvalues, so that one of the eigenvalues is 1, then the other one must be -1, or the second possibility is that both eigenprojections of T are Hermitian. This was already known before this general result, and this is something that we should emphasize here because it is going to be an important result for further study. Let us notice that we can always assume that one of the eigenvalues is 1. If not, we simply multiply a given isometry by the conjugate of one of the eigenvalues. Let us also mention that if we have a 3-point spectrum isometry, so that the spectrum is 1, lambda, and me, then lambda and me are conjugated to each other, or one of them is the square of another one. Or the other possibility is that all 3 eigenprojections of that isometry are Hermitian projections. Any complex Banach space admits Hermitian operators, at least scalar multiples of the identity operator. But C-star algebras have plenty of Hermitian operators. They have the form X maps to AX plus XB for some self-adjoint A and B in the multiply algebra of A. In any JB star triple, the operator A box A is Hermitian. But A box B is not necessarily Hermitian. It is Hermitian if and only if it is symmetric. And A box B plus B box A is always Hermitian. But Hermitian operators appear as eigenprojections of isometries. So we have a really nice characterization of Hermitian projections given by James Jamison. A projection P on a complex Banach space X is Hermitian if and only if P plus lambda times I minus P is an isometry for all modulus 1 complex numbers lambda. And directly from this definition, from this characterization, we see that P is Hermitian if and only if its complementary projection I minus P is Hermitian. And clearly, this characterization implies that Hermitian projections are bicontractive. And in JB star triples, any bicontractive projection is the average of the identity with an isometric reflection. In other words, any bicontractive projection is an eigenprojection of a 2-point spectrum isometry whose spectrum is equal to the set 1 and minus 1. So Hermitian projections are bicontractive. How to recognize Hermitian projections among bicontractive ones? Here we have a characterization that tells us that a bicontractive projection P is Hermitian if and only if the range of P and the range of the complementary projection I minus P are complementary to each other in the JB star triple sense, which is described here. There are bicontractive projections that are not Hermitian. Here we have a simple example. It is a projection defined on 2 by 2 complex matrices that sends such a matrix to the corresponding diagonal matrix. So these two classes do not coincide, Hermitian projections and bicontractive projections. However, if we consider only rank 1 linear projections, then these two classes are the same classes, bicontractive projections and Hermitian projections. And even more, they lead to the decomposition of a JB star triple as the direct sum of two JB star triple subtriples, so that one is related to the image of P and the other one to the kernel of P. What about Hermitian projections on some important JB star triples? For example, on B of H, any Hermitian projection has the form X maps to PX or X maps to XP for some self-adjoint projection in B of H. This result can be obtained quite easily knowing that Hermitian operators on C-star algebras, and B of H is a C-star algebra, have the form X maps to AX plus XB. Stacho and Zallar obtained this result for B of H, as well as the following two for S of H and A of H, using the algebraic techniques. They relied on the JB star triple theorem. In their paper, they called the class of Hermitian projections generalized bicircular projections, because at that time they were not aware that generalized bicircular projections are in fact projections that are Hermitian operators. So after Jamieson characterization, we can now use this notion of a Hermitian projection. S of H admits only trivial Hermitian projections, 0 and the identity operator. But surprisingly, antisymmetric operators have plenty of Hermitian projections. And now it turns out that whenever we have an arbitrary complex Banach space X and a linear isometry T on X, so that it has 2-point spectrum 1 and lambda, then T is periodic, which means that lambda is some mth root of unity, or both eigenprojections are Hermitian operators. We know that in the case of JB star triples, this lambda must be -1. And it is the case for a large class of complex Banach spaces. In fact, whenever we have some nice complex Banach space, nice in the sense that it has a name, then lambda is -1. We don't know any complex Banach space, let's say with a name, in which this lambda is anything else but -1. But Lin constructed, let's say artificially, for any primitive mth root of unity, a complex Banach space X and an isometry T on X, so that the spectrum of T is 1 and that mth root of unity. So T is periodic of period M for any given M. In this talk, we shall be interested in those complex Banach spaces in which any linear isometry T with 2-point spectrum 1 and lambda is such that lambda is -1, or the eigenprojections of T are Hermitian. I have just mentioned that we have many examples of such spaces, but since this is a non-associative seminar, it is sufficient to think of JB star triples. And this result by Botelho and me concerns periodic linear isometries on these spaces. So we go from 2 eigenvalues to an arbitrary number of eigenvalues. Here, an isometry has period M, and we have the spectrum lambda 1 to lambda n. Let us denote by mi the least common multiple of the order of all lambda j except lambda I. Then one of the following holds. T has a Hermitian eigenprojection, or all these least common multiples are mutually equal and equal to M, or they are all equal and equal to M, except one of them, which is half of M. But if we have an isometry for which 3 holds, we can multiply it by the conjugate of lambda j to get a new periodic linear isometry with the same number of eigenvalues, so that 2 holds. So we can always reduce the case 3, the third possibility, to the second one. So what does this theorem say? Well, for large periods, it can be complicated. But let us illustrate this result for, let's say, periodic linear isometries of period 6. Because 6 is a nice number. It is not prime, but it is the product of 2 smallest primes. So we can consider that case. We assume, without loss of generality, that one of the eigenvalues is 1. We also assume that none of the eigenprojections is Hermitian, because whenever we have Hermitian projections, there are more possibilities. But what remains is that the spectrum of T can be only one of the following. It can have 3, 4, 5, or 6 eigenvalues. Here beta denotes the primitive cubic. So if we consider the case of 3 eigenvalues, one can say that we have 3 cases. But in fact, we have only one. If we say that the first one is the main one, then the remaining 2 can be obtained from the first one by multiplying this first set by the conjugate of the remaining 2 eigenvalues that are not 1. In the case of 4 eigenvalues, we have 2 main cases, 2 main possibilities, the first 4 and the second 4, the last 4. If we have 5 eigenvalues, we again have 1 possibility. But one would say, since we have 5 eigenvalues, 1 is 1, so there are 4 that are different from 1, by multiplying this first set by the conjugate of these 4 eigenvalues, respectively, we are going to get 4 additional cases, 4 additional sets. But in one of these sets, one is not an eigenvalue, so it is omitted. Or the final possibility is that when we get the complete set of 6 roots of unity. We're going to see that these blue cases, in fact 3 of them, can happen in C0 of omega. And we're also going to see that the remaining 2 ones, these red ones, cannot happen in C0 of omega. First of all, we can always find an isometry of period n so that its spectrum is the complete cycle of n roots of unity. We also say that T has full spectrum. Here we have such an example for any positive integer n. Let us notice that this is a composition operator. So in fact, it is a star isomorphism. We can omit the word Jordan because of commutativity. If we have 3 eigenvalues and omega is connected, then the only possibility is that the spectrum is equal to the complete cycle of cubic roots of unity. So it must be of period 3. If we have 4 eigenvalues, then such an isometry is not necessarily of period 4. Here we have a nice example in which we have an isometry of period 6, but with 4 eigenvalues. Here the space omega is the unit cube, so that one of its vertices is in the origin, union the segment that passes through the origin. So the cube is the set A and the segment is the set B. We define phi to have period 3 on A, on the cube, and period 2 on the segment that is on B. So phi has period 6. The corresponding composition operator also has period 6, but its spectrum has only 4 eigenvalues, which is in fact the complete cycle of square roots of unity union the complete cycle of cubic roots of unity. So this case can happen, and the derived 3 sets of eigenvalues can also happen. So whenever we have 4 eigenvalues, the spectrum can be either the complete cycle of 4th roots of unity, which can happen, or the set as in the previous example, and the remaining 3 that can be derived from this one. When we have 5 eigenvalues, then we can get the complete cycle of 5th roots of unity, which is in fact the only case if T is a composition operator. Or there are 4 other cases that can also happen, as we are going to see. The space omega here is defined in a complicated way. It is the union of 5 sets that are defined using the spherical coordinates. We are going to see the picture, so it is going to be clear. But for now, let us emphasize that phi is defined to have period 3 on A1, A2, and A3, and period 2 on B and C. We have to define the weight function, which is not the constant function, but it is the constant 1 on B and the primitive cubic on C. The corresponding weighted composition operator has period 6 because phi has period 6. And this is our set omega. And this is the set of eigenvalues of the isometry T that we have just defined. The first set of eigenvalues, the complete set of the complete cycle of primitive cubics, cubic roots of unity, is obtained from the sets A1, A2, and A3, because on these sets, phi has period 3. The remaining 2 sets come from B and C. We start from the complete cycle of square roots of unity, 1 and minus 1. In the case of B, we multiply this set by 1, because it is the weight function on B, and by the primitive cubic beta on C. So this is how we get this set of eigenvalues. Let us only mention that, because we are going to recall this example, that we can find an example of a composition operator of period 12, which does not have full spectrum. Its spectrum is equal to the complete cycle of cubic roots of unity union the complete cycle of 4th roots of unity. And now let us go back to the setting of JB star triples. And from now, we shall be interested in real linear surjective isometries, or equivalently, those surjective isometries that fix the origin. According to the Mazur-Ulam theorem, they must be real linear. With the additional assumption that the bidual of A does not have a non-trivial Cartan factor of rank 1 as a summand, then A can be decomposed as a direct sum of 2 JB star subtriples, A1 and A2, so that the isometry T restricted to A1 is complex linear and restricted to A2 is conjugate linear. and both these restrictions preserve the triple product. This result can be applied to C-star algebras. When they are unital, then this complex linear restriction is in fact a Jordan star isomorphism multiplied by a unitary, and this conjugate linear restriction is a Jordan star isomorphism composed with involution and multiplied by a unitary. In Dunk's paper, the author was interested in JB star triples. So this theorem is his main result. But this corollary appeared as the last result in that paper, which is in fact a direct consequence of this theorem. And probably it is, I think, given without the proof. So probably it did not receive as much attention as it should, because later it was reproved by Hattori and Watanabe. And this is the formulation that they have in their paper. Let us emphasize that this T of identity, the image of the identity, is a unitary element in B. So now, when we go back to Caddison's result, which is for unital C-star algebras, we immediately think of Patterson and Sinclair's generalization for not necessarily unital C-star algebras. They in fact obtain the same result with some necessary adjustments. So this was the starting point for me and a group of my co-authors, 7 of us ladies mathematicians. And this is the result that we have obtained. In fact, this is the result of the same type, except that a unitary U and the central projection P are not in B, but in the multiplier algebra of B. The idea of the proof is the following: to apply the result by Hattori and Watanabe to biduals. But it remains to prove that U and P live in a narrow, let's say, house of the multiplier algebra of B, and also that J, when restricted to A, has the image B. We have been also interested in the spectra of real linear surjective isometries of C-star algebras. However, the situation here is different, because in the case when we have a real linear operator, its spectrum can be empty. This is why we introduce, we work with the so-called complex spectrum. It is a known concept. First, we start with the real Banach algebra X, say with identity. We complexify it by defining the complex multiplication and the multiplication. In fact, in both cases, we mimic complex multiplication. We define the new norm that makes this complexification into a complex Banach algebra with identity, and we embed a real Banach algebra X to its complexification by sending A to the pair A0. The complex spectrum of A is then the spectrum of A0 in the complexification, the spectrum in the usual sense. So here we assume for simplicity that the unitary U is 1, but we also need an additional assumption that J of PA is Pj of A. The reason for that is that we want to enable restricting T to a linear and conjugate linear part. So in fact, this J of PA is Pj of A is equivalent to the assumption of the square of T is equal to the square of J, which is also equivalent to the assumption that the square of T is linear. So when we think of this condition, that the squares of T and J coincide, we start from any lambda which is in the spectrum of J. it implies that either lambda or minus lambda appears in the complex spectrum of T. But this result, in fact, tells us that any eigenvalue of J is in the complex spectrum of T. And we also know which of these eigenvalues also come with the opposite sign. These are those that somehow arise from this conjugate linear part of the isometry T. So what about isometries that satisfy this condition? The simplest one is the composition of a Jordan star isomorphism and involution. For such a mapping, the complex spectrum is equal to the union of the spectrum of J and minus spectrum of J. Then also, if we have a real linear isometry, which is induced by J, then T is periodic if and only if J is periodic. We also know that either T and J have the same period, or the period of T is twice the period of J. And now let us illustrate our result with some examples. Here we start from any primitive nth root of unity. We consider a star isomorphism, a composition operator, J, so that Jf sends Z to f of tau of Z, where tau is the primitive nth root of unity. We have already observed that such J has period n and that its spectrum is full. It consists of the complete cycle of nth roots of unity. If we compose J with involution, then again we get the full spectrum, but not necessarily equal to the spectrum of J. If n is even, then the complex spectrum of this composition is the complete cycle of nth roots of unity, but when n is odd, it is the complete cycle of 2 nth roots of unity. So in this example, both J and T have full spectrum. In this example, we have again the composition of a Jordan star isomorphism and involution, and we assume that such an isometry has period 6. We have seen such concrete examples. Then J can be one of the following. We have 6 possibilities. The first and the last possibility are full cycles. So the complete cycle. So the spectrum is full in the first and in the last case. But in the remaining 4, the spectrum of J is not full. However, the complex spectrum of T is the complete cycle of 6 roots of unity, so it is full, no matter whether J has full spectrum or not. And also another example that I have just mentioned in one of my slides, when we have the composition operator of period 12, which does not have full spectrum. In fact, the spectrum is the complete cycle of cubic roots of unity, union the complete cycle of 4th roots of unity. So it is not full. And when we compose J with involution, the complex spectrum of that composition is also not full. So we see that even in this, let's say, simplest case that we have studied, there are various possibilities that can occur. So I hope that I have succeeded in showing you how non-associativity helps associativity and how this really beautiful Kaup's generalization of the Banach-Stone theorem can be a useful tool in studying isometries in various operator algebras and operator spaces, and in particular C-star algebras. So thank you very much for your attention.
So thank you, Diana. Thanks a lot for the nice presentation. I enjoyed a lot. I'm particularly I'm particularly quite related to Cope's theorems and all this stuff. So it was very, very easy to follow. So I should ask anyone in the audience has any question or remark or would like to say something about this? Questions? Yes, someone Florin Nichita is asking about the references. Diana, can you
Well,
check?
these, let's say, main results that are ours are still in preprint phases. So I hope they will be posted soon to archive. They have not been submitted yet to a journal. So it is not clear when it will appear in some journal. So these are the papers with Gaiching Wong and two of his students and postdocs. And so this is the main core, let's say, for this result and the main motivation. And also these results by 7 of us ladies mathematicians. I should emphasize that maybe it sounds strange, but we have started our collaboration as a research group within the workshop Women in Operator Theory, supported by the Lawrence Center in the Netherlands. So we have been working ever since that time, and we are also writing some other papers on other topics. So it is a very interesting collaboration that we do exclusively online because we are from 3 different continents. So it is an interesting fact.
So you are fighting against again
Yes.
also geographical difficulties, not only mathematical difficulties. Okay, any other question from the audience? No, if that is not the case, I have just a small comment or something. I listened to you saying that you are much more interested in on the first three Cartan factors, type 1, 2, and 3.
Yes.
Let me simply say, by the way, that the spin factors are not only popular in physics, but they are also JC star algebras. There is a natural construction by the subtriple or the Jordan algebra generated by an anti-commuting set of symmetries. So they are quite related to Lorentz group, Lorentz geometry. So they are also operator spaces somehow. So they are naturally connected to that. And I agree with you that all the exceptional Cartan factors are far away from what we usually know. So it was already found by Wigner, Rosenthal, and I think Jordan, Wigner, and von Neumann, of course. I had forgotten that. Just one question, which I was just considering. In most of your examples, when you are computing your spectra and so on, you are dealing with C naught of omega. I mean, you
Yes.
are actually living and taking advantage of the operator, the composition operators in order to compute that. Is there anything similar to that in the non-commutative setting in which you could handle the concrete spectrum for mapping in such a case, or is it too difficult? Or maybe they are.
Well, we have not done that for
Okay.
some other cases because, well, when you go further, it turns out to be really difficult, at least for us. We were also not very happy by introducing this additional condition that the square of an isometry must be linear. But in fact, we found some counterexamples showing us that the situation is not really clear, let's say. At least we cannot see any rule that holds. So also we were, well, maybe we were stuck with something that we knew. But anyway, there is much more that can be done. But as I said, even in this case, it turned out to be difficult. However, probably it will be possible to make nicer and better results, I hope.
Okay. So, and just one question. In the paper by Keller and Rosenthal,
Yes?
that Rosenthal is the famous Haskell P. Rosenthal. I didn't have time to find the reference on the web. Is that the same Haskell Rosenthal?
It is this Keller and Rosenthal.
Yes. Is Haskell Rosenthal, or because you simply wrote P. Rosenthal?
Oh, this is Peter Rosenthal, which
Well, I will check. I will
yes,
check on.
I think. Yeah, yeah. It is
I
a
didn't
short.
know.
It is a short paper. I think 4 pages. It is quite cited, I think, and many people cited that result. But during our work in our research group, we became quite suspicious about the proof. So it resulted with the Shiho's extension and the new paper.
Yes, I'm sure it is not a big surprise. Okay. Well, I have no other comment. I hope no one from the audience is willing to pose any new question. No, if that is not the case, I think we should thank the speaker again.
Thank you
So,
very much. Thank you. Thank you.
so it was a big pleasure to
Thank
be
you.
here. So I think that's all for today. I hope to see you in some coming events in
I hope so.
non-associative algebra seminar, but also in person. I hope we can meet all together sometime in the future. So
That would
thank you
be
so
nice.
much. Thank you so much to the speaker and to the audience for spending the time coming here. So bye-bye. That was all for
Thank
today.
you. Bye. Bye.
Bye-bye.